Good morning, AP Physics 2 class, first period, Davidson Academy. My name is Mr. Claxton. Nice to see you today. This is our first of a series of videos you'll be watching as you finish out the school year, or at least for the next week or two, maybe longer, having class online. Not terribly happy about this, as you aren't either, but it is serious and we need to have class. So we're going to. Now, some of you are concerned that the school told you that school would not resume until Wednesday, and I am requiring you to watch this on Monday, March 23rd. It's an AP class. School, the spring break is over. School was going to resume on the 23rd anyway. We got a little bit behind by losing some time back before spring break when they canceled school. So no, we're not going to waste another day. We're going to move on. Hope you're all okay with that. Nice to see that you're all here today. Is Lucy here? Yes. See, we're all present. Sophia is present as well. She hasn't said anything yet, but she will. And I will be very grateful. You know how much I wish I could see you right now. Okay. Anyway, we're going to finish out the year. We have one unit remaining, and then after that will be the review. Be nice if we were back together by then, but we'll see. We will see. Everything I've planned for the first week is in topics. If you go to Blackbaud and go to our class page, whatever that is, and click on topics. Now, some teachers have used topics. Maybe you're familiar with it. I've never used it before, so I probably messed it up. But go to topics, and there is one called Online Class Week 1. There's a great picture there that kind of summarizes, the way things are. But if you go there, what you'll see is instructions, and you will see assignments for each day, at least in the first week, is in that topic. And it will tell you what your assignments are for Monday. It will tell you that they are due on the next day. In this case, the assignments for Monday will be due on Tuesday by 12 o'clock. And how do you turn in your assignment? There's probably a fancy razzle-dazzle way to do that, but what I'm asking you to do is take a picture of the paper you wrote the answers on and you worked the problems on. Take a picture and email that to me, jclaxton@davidsonacademy.com. And that email needs to get to me by noon on Tuesday for you to get the homework credit. All right, and homework for the first day is I believe it's A and B, but it's there in topics. Whatever it says, do that. The syllabus is also there in topics, although you can get that under syllabus in Blackbaud as well. And you probably still have it on a piece of paper somewhere. Okay, as we go through this first lecture, I'm going to be introducing to you nuclear physics. This is chapter 31. And 32 that will be involved in this final unit, nuclear physics. We just finished a unit on atomic physics. We talked a lot about electrons that can gain energy and pop up to higher energy levels, and when they drop back down, they emit photons. All right, we studied all that. That's atomic. That's the atom. This unit focuses on the nucleus of the atom. The protons and neutrons, not so much the electrons. Now, throughout this lecture, I'll be pausing it, and the only way I know to pause it, I don't know, I'll probably mess that up too. So, Claire, which one of these buttons do I push to pause it? I think it's this one. We'll find out. I think that worked. Thanks, Claire. Now, we start, and I'm going to rush through this because these are things that you know. The atom is made up of protons and neutrons in the nucleus, and there are electrons and the various energy levels spinning around the nucleus. And you know all of this. These particles in the nucleus are called nucleons. Nucleons are particles in the nucleus. So that the term nucleon would include protons and neutrons. Okay. Now, there's a very important chart in your textbook, chapter 31. It's on page 958. And you need to turn there and look at this chart, but I'm showing it to you up close right now. It is, I don't know, I guess you can see that. It is a chart of charges and masses of the various particles. And notice some things about the numbers for the masses in particular. And some of you are going to love this because you don't like rounding off. You don't want to round things off very much. Well, look, there are, I don't know, 7, I think, significant digits in those masses. This is maybe the first place in 2 years of physics that we will finally get to a place where I'll say, don't round it to 3 significant digits. If you do, the difference goes away. The difference in masses, you don't see, say, between a proton and a neutron, you don't see the difference in 3 significant digits. So, yeah, we're going to keep the long version of these numbers in this chapter. All right. You know what we didn't do when we started class was we didn't pray. I'm going to pray now. Lord, I ask you to help me to teach. I ask for each student watching this video to learn what I'm trying to teach and keep them safe. In Jesus' name, amen. Commentary at the end of the video if there's time. By the way, I'm going to try to limit these videos to 30 minutes, just so you know. It's my goal. I've already used up about almost 7.5, but let's move on. It might be less than 30. That's my hope. All right, so you know all that, and you can look in the chart and see what those masses are. Now here's, hold on. All right, here are things that you know, I hope. Atomic number, by the way, this board I'm writing on belongs to Bob Campbell. I borrowed it from his band room with his permission. I'm standing in my downstairs den at my house right now. I'm not at school. Sorry if that bothers you. Yeah. And this is going to be my classroom for a while. Things you already know. Atomic number is a number of protons. If we use the word atomic mass, that's protons plus neutrons because they have about the same mass, and it's a whole lot more than an electron. All these are things you know, I believe. And so if you see a symbol like C for carbon, and over here there is a 14, and over here there's a 6, you'll know that C is the symbol of the element, 14 is the mass number, and that would be in U's, atomic mass unit. We would say the mass is 14 U's. And the U stands for atomic mass unit. And that's protons plus neutrons. And the 6 down here is the atomic number, so that's the number of protons. Therefore, if you need the number of neutrons, you could simply subtract these numbers, couldn't you? This particular isotope of carbon has 8 neutrons. Okay, all those are things that I'm hoping you remember from chemistry, or you just know because you've been around. Yeah. Okay. Now, if you take that knowledge and apply it to that chart I showed you on page 958, I think, or 959, I don't know what page it was on. there's some interesting things that begin to show up. And let's start with the first question that you've had, and you probably know the answer, but it's a question that bothers you still. I know Sophia's bothered by this, aren't you? Yes. Is that the nucleus of an atom is made up of protons and neutrons. The neutrons don't have a charge, of course, they're neutral. The protons are positive. Like charges repel, and yet they stick together. The electrons are out here, and so the reason they don't go away is the positives are attracting them, the opposites attract. But why do two protons just sit next to each other and like they're friends? They're not friends. They're repelling each other, but something stronger than that repulsive electrical force is holding them together. And you might remember the various types of forces. We have learned electromagnetic is the catch-all. That's the kind of force that includes electrical and magnetic, but also just push and pull forces. And they're all included in that category of forces. Another type of force is gravitational, and gravitational forces are attraction between masses. We've talked about that in Physics 1, actually. And then the third one is called, the third and fourth are called nuclear forces, and sometimes they're put together. But what I'm going to do is mention the strong, here you go, strong, strong nuclear force. Now we'll get to what's called the weak nuclear force when we get to chapter 32. That involves radioactivity, chapter 32. But the strong nuclear force is the name of the force that holds the nucleus together. It's called strong because it's stronger than the electrical force of repulsion. It overcomes that force, it's greater, and it holds the nucleus together. Okay, you need to know that term. Strong nuclear force holds the nucleus together. Now, that's one unusual thing, and there's not, I know Sophia has a question about that. Well, what is it? Nobody knows what it is. If they knew what it was, they wouldn't name it the strong nuclear force. That's what you name something when all you know is that it's in the nucleus and it's strong. Okay. There are theories about that, but that's not our point today. So that's one unusual thing about the atom. That there's a force greater than an electrical force and it holds the nucleus together. Another interesting thing about the atom comes from that chart on the first page of the chapter. And I'm going to give you some numbers, and you're going to be astounded by this, I'm pretty sure. Let's talk about helium, which is the picture I just had up there. It's two protons and two neutrons, and there would be two electrons spinning around that. Helium, the actual mass of a helium atom, well, it would round off to 4 because 2 protons and 2 neutrons. 2 plus 2 is 4. But the actual mass, if you keep a bunch of digits, is 4.0026 atomic mass units. Now, that's not an average of the isotopes. That's the actual mass of the atom. Now, here's the interesting thing. Use the chart on page, whatever page that was. Okay, that was page 958. Use that chart and add up 2 protons plus 2 neutrons plus 2 electrons. And all those masses are there in that chart. And if you add those masses up, yes, in atomic mass units, use the third column. If you add those together, you will get, I've done this for you, but I'm sure you'd want to check my math. And if you add those together, you get 4.0 0.0329979 atomic mass units. So here's what's confusing you. This is confusing you a little bit, isn't it, Jaden? Jaden? Jack, would you give Jaden a little nudge? Don't hit him hard. Okay, Jaden, look how confusing this is. The mass of helium atom is this, but if I add up all the parts, 2 protons, 2 neutrons, 2 electrons, I get this, and this is more. When you take those 6 particles and put them together into an atom, the mass decreases. Oh my goodness. How can it have less mass? Well, the reason it has less mass, my friends, is going back to that strong nuclear force. Now that's a force, but where there's a force, there has to be energy. And it turns out that it takes energy to hold protons together. In fact, it takes energy to get them to move toward each other, because they don't want to do that. Where does that energy come from? The energy to hold the nucleus together. Where does it come from? It comes from mass. Mass turns into energy. That's why this mass is a little bit less. Some of the mass that you had with the 6 particles down here, some of that mass turned into energy to hold those doggone protons together. Yeah. It has a name. It's called binding energy. So let me put this back together in a way that you can see it. Probably should pause, but I'm not going to. Yes, I will. Okay, here are the same numbers. I just wrote them this way so we could see that we're subtracting them. Up here again, you have the helium, the mass of the helium atom. Here you have the mass of the 6 particles added up. And of course, I just did that backwards. Okay, hold on. This is the 6 particles, which is more. This is the helium atom, which is less. There. And if I knew how to edit video, see, I would take that out, but I don't know how to edit video. Okay, so if you subtract them, you get this. Here's the difference. This has a name, as I mentioned. It's called the binding energy. Sometimes it's symbolized simply as delta M, because you get binding energy by the difference, subtract the masses. It's the amount of mass that went away. No, it's not called the binding energy yet. See, once again, I would be, we'll get to the binding energy in a minute. This is called the mass defect. There you go. We'll get to binding energy in just a second. But this is called the mass defect first. The mass defect, or delta M. Okay, now it makes sense to you. Now you're getting it, aren't you? Aren't you, Sarah? How much time do we have left, Sarah? Okay, we're good. Mass defect is the difference in the masses. The particles add up to a greater mass, so subtract that minus the actual mass of the helium atom, and you get the difference here. So the question is, where did that mass go? And the answer, as I mentioned before, is this amount of matter, this mass, turned into energy. And that energy is what holds the nucleus together, or draws the particles together. Okay, well, how do I find how much energy that is? And that's called the binding energy. Here we go. Binding energy is the amount of energy it took to bind the particles together. And where did that energy come from? The mass defect. Matter turned into energy. If you want to calculate the binding energy, you get to use this equation that you've been wanting to use ever since you were in elementary school, and no teacher would ever let you do it because you weren't ready. But now you're ready. E equals mc squared. E is for energy. M is for mass. C is the speed of light, 3 times 10 to the 8th meters per second, but it's c squared. And if you plug that amount of mass into the m, this amount of mass, which is the mass defect, into the m, multiply it by c squared, you'll get the amount of energy that it took, the binding energy, to pull those particles together. Now, by the way, if those particles come apart, it releases that much energy. We'll get to that later. All right, here's some important things about using this equation. The units. Doggone the units. If you're going to use 3 times 10 to the 8th meters per second and square that, which is what the only number you know for C, then the M has to be in kilograms because that's SI units, meters per second. The SI unit for M is the kilogram, and the E will come out in joules, the SI unit for energy. Everything in SI units. So this number up here was in atomic mass units. If you're going to use that equation the way I've just taught you, you've got to convert this to kilograms. And you can do that using your equation sheet, which I don't have available at this instant. I'm not going to pause it, but on your equation sheet, it tells you, and it's not hard at all, to convert use to kilograms. Okay. You're basically going to divide that by the mass of a proton, but you'll see that on the constant page if you need to do that. The reason I'm not going into that and the reason I'm not going to take time is that we don't usually do it that way. We don't usually use joules and we don't usually use kilograms. We use atomic mass units for mass instead of the kilogram. And I'll bet you could guess then what unit we prefer rather than joules for energy. What do you think it is, Steve? What unit for energy, Steve? Steve, what'd you say? Correct. The electron volt. Electron volts. However, not just the electron volt, it's going to be the mega electron volt. So let me show you how this is going to work. I'm erasing those numbers, but I've still got my mass defect up here. Someone, not really Albert Einstein, but someone said, well, let's take Albert's equation and put it into units we like better. If that's kilograms, we know how to convert that to atomic mass units, and that's speed of light squared, which is meters squared over seconds squared. Can't we take kilograms and meters per second squared and come up with some number that will always work, where I can take the mass in U's and multiply it by some constant that fixes the units. That's one reason we have constants in equations, that constant will convert kilograms to U's, and it will convert the meters squared over seconds squared as well. And that'll all be there. So instead of C squared, we'll have that number. And when we do that, we'll get electron volts. Only know it's going to come out to be mega electron volts. That number is 931.5. You don't have to do the math. It's been done for you. In fact, that number is on your equation sheet. However, no, I think this is the number in your textbook. The equation sheet on the constant page will just use 931. So you're free to use 931, certainly on the AP exam. If you do homework, I'd probably use 931.5 because the textbook is using that when they tell you what the correct answers are in the back. Not that any of you ever look back there, but some of you might. Okay. Kyle's going to look back there to find at least one answer. I'm pretty sure, aren't you, Kyle? Yeah, that's what I thought. All right. Okay, so let's just look at a sample problem. We've got a few minutes. I'm going to pause it and put a problem up here. I'm not changing the problem. I just rewrote it to have room. Here's the mass defect for helium. We've already subtracted to get that number of atomic mass units. The question is, what's the binding energy for the helium atom? And what I have taught you, based on this equation, we're not using the speed of light squared. Instead, we're going to put it in atomic mass units, which is 0.03379. That's atomic mass units. And then we're going to multiply that times 931.5. And when we do, we get the answer, which is 28.3. Now notice my final answer, I rounded to 3 significant digits. You don't need more than that at this point. But the energy comes out to be 28.3, but it is mega electron volts. When you see this number 931 on your equation sheet, you'll notice mega electron volts is in the unit. So that is, and mega means 10 to the 6th. Hopefully you remember that. So that's the amount of energy for the entire atom. Now let me warn you, sometimes the question is, sometimes instead of that question, it will say, what is the binding energy per nucleon? So just look for that. If you see that, that's not a hard question. You simply take the total binding energy and divide it by the number of nucleons, which in the case of helium is 4. 2 protons, 2 neutrons. So if that's the question, you would simply take your 28.3 and divide it by 4 nucleons, and you get something like 7.07 mega electron volts per nucleon. So that's the amount of energy per nucleon it took to pull those 4 particles together to form a helium nucleus. All right. Those kind of questions you'll get in your first homework assignment, which is due Tuesday by noon. Now, one final thing to mention to you in the few minutes we have left, and that is another chart, just for the concept. This chart is on page 961. It's that chart. There's a graph where you see, what do you see? You see neutrons on the y-axis and the number of protons on the x-axis. And the question here is about stability. Some atoms are stable. They're not going to come apart at all. Some are unstable, which means radioactive. The blue dots represent atoms that are stable. If you go back and look at that chart, I've removed it from the screen, but open your book to page 961. If the atoms, neutrons, and protons align with those blue dots, that's a very stable atom. But if they're somewhere else, they don't. It's not stable. And the red line shows you where protons and neutrons are equal. So it starts out, for carbon, 6 protons, 6 neutrons, it's stable. And then the small numbers, the blue dots are on the red line. But as the atom gets bigger, it needs more neutrons. Neutrons for large atoms, you need to know conceptually, neutrons for large atoms, more neutrons in the larger atoms produce stability. Fewer neutrons, less stable. You need more neutrons and protons in the big atoms if you want to have a stable nucleus. Otherwise, it's radioactive. So you can use that chart to kind of get an idea of when an atom might be radioactive. All right. Final words for today. So if you don't want to hear my final words, feel free to stop. But doggone it, this coronavirus thing has got us all in a tizzy. That's not unfounded. The science is very real. This is a highly, highly contagious virus. Easy to get it. You just touch something that somebody else touched and you've got the virus. That's why we quarantine. There's no real treatment. There's no immunization for this. Our only tool to fight the coronavirus is quarantine. That's why you're staying at home. I hope you're staying at home. Every time someone from your home goes out and comes back, there's the potential that they're bringing the virus with them. So I'm just telling you to take precautions seriously. I don't want any of you to get sick. Oh my goodness. I don't want you to bring the disease to someone else you love. So stay home. Watch my videos. Do the homework. Take pictures and turn it in. Check topics to see what's coming up. It's all in Blackbaud. I will not be sending you emails with the assignments. They're in topics. You, though, are free to email me at any time of the day. However, I will only be checking my email from 8 to 3. But you ask me a question, I will try to respond to it. I will either respond in an email or I might just add that to the list of things I want to talk about in the next day's lecture. So I will be doing that. I will be reading your emails and trying to answer your questions as best I can. This whole thing is new. We don't know what's going to happen. I don't know how this is going to work. I'm sure I'll be revising the way I'm doing it, perhaps even this first week. So we'll see what happens. I love all you guys. Hope the best for you. Stay safe. Bye.